Hello, this video's about how to translate between matrices, that is tables of numbers, diagrams which show what those matrices do as linear transformations, and words which say what that linear transformation is. And being able to translate between the three ways of describing the same thing is really useful in maths, because sometimes something that's really difficult to work out if you describe it one way becomes really easy when you translate and describe it in a different way. So you can do sums with the tables of numbers, which you can't really do with just descriptions in words. So I put one example up already. In words, rotating 90 degrees anticlockwise. So 90 degrees anticlockwise, like that. Or here, rotate that 90 degrees anticlockwise. Right, in the diagram, we always just look at 3 points. The origin, 1, 0, and 0, 1. We use those 3 points because they're the simplest ones to deal with, and they will tell us everything. All you need to do is look at those 3 points and you will know what it does to all other points. You notice we write the coordinates of the points as a column vector, not as a row. That's just the convention when we're doing this sort of calculation. So that's the point 1, 0 on the x-axis. That's the point 0, 1 on the y-axis. And the red arrows show what happens if I rotate anti-clockwise. The origin stays where it is, and the origin stays where it is with all these transformations. So one of these 3 points will always stay where it is. But this one moves up to 0, 1. 0, 1, meanwhile, has moved round to -1, 0. We can find the matrix simply by putting in the first column of the matrix where 1, 0 goes to, 0, 1. And in the second column of the matrix, we put where 0, 1 goes to, that's -1, 0. Okay, so all those 3 are different ways of describing the same thing. Let's look at what rotating 90 degrees anti-clockwise would be. No, rotation 90 degrees clockwise, sorry. The opposite, okay? Rotate 90 degrees clockwise. There we've got our 3 green starting points. What happens to this one this time? Well, it rotates not up that way, but down this way to there, to 0, -1, 0 across, and -1 up, or 1 down, in other words. This point, 0, 1, rotates 90 degrees, so it ends up at 1, 0. So, same method for finding the matrix. First column is where this point goes to. That point goes to 0, -1. The second column is where this point goes to. That goes to 1, 0. And there you are. For the third one, let's try starting off from the matrix. So let's see what would happen if we had -1 there and -1 there. Right, okay. The origin stays where it is, as always. This point goes to the point described by the first column. So it goes to -0, -1, which is there. So that goes to there. This point here goes to the point described by the second column. So that goes to -1, 0, 0. Right, so we see they flip across that way. What sort of transformation can make that happen? Well, it's a reflection in that line there, in the line y equals minus x. A little check, reflections always have a negative determinant, so you just check, is the determinant of that negative? Yes, it is. 0 times 0 minus 1 times minus 1, minus 1 times minus 1. 3 minuses gives you a minus. So the determinant of that is minus 1. The determinant of those two is 1. And the determinant of rotations is always 1. It's always positive if it's just a rotation. Okay, I'm going to rub these out and we're going to try a few more. Okay, so next one we'll try is reflection in the y-axis. Okay, so we do our diagram. We mark in our 3 points and their coordinates. That's 0, 1, the 1, 0, and that's 0, 1. And we think, well, where are these points going to go to if you reflect them in the y-axis? The origin stays where it is, that stays where it is because it's just on the y-axis. This one reflects over here to here, which is what? It's minus 1, 0. The matrix we can find from the fact that the first column is where this point goes to, that's minus 1, 0. The second column is where that point goes to, and it stays where it is, 0, 1. So there's the matrix. If we check that the determinant is minus 1, that gives us a little extra check because reflections always have a negative determinant. Okay, here's another. We'll start off with this matrix. Okay, that's the matrix. Let's do a diagram again. Put in the coordinates. Right, so what happens with this one? The origin stays where it is, as it always does. 1, 0 goes to the point described in the first column. The point described in the first column is 1, 0 again, so this one stays where it is. What about the second point, 0, 1? That goes to the point described in the second column, which is 0, 1, 0, 1 again. So that stays where it is. So all 3 points stay where it is. I've told you these 3 points describe everything. So this means leave everything as it is, which is why it's called the identity matrix or the identity transformation. It's the equivalent for matrices of 1 with numbers. You multiply anything by 1, you just get what you started with. You transform anything by this identity matrix and you just get what you started with. Another couple of examples. Right. We will try one here which hasn't just got ones in it. So it's 2, 0, 0, 3. So we draw the diagram. We mark in the 3 points. we label their coordinates and we look to see where they go. This point goes to the point described in the first column, which is 2, 0, which is out here somewhere. This point goes to the point, this point here goes to the point described in the second column, which is 0, 3, which is up here somewhere. So the origin stays where it is. So you can see what's happened is that everything's been spread out, and we can describe this as a scaling twice times the width and 3 times the height. If it had been just 2 there, so you have just 2 here, so this point goes to 0, not 0, 3, but 0, 2, then everything that is scaled up the same extent. The heights are scaled up twice and the widths are scaled up twice. So it's just a scaling of everything 2 times as big. It's just a magnification. One more. There's a matrix. Here's the diagram. Here are the 3 points. Here are their coordinates. Here is where they go under this transformation. This is where this transformation takes them. The origin stays where it is. 1, 0 goes to the first column. 1, 0, that stays where it is. 0, 1, it goes to 1, 1, which is there. So that moves across to there. Those 2 stay where it is. And what that means is if we had a triangle like that, it would change into a triangle like that. And that is called a shearing. It's like the Mona Lisa picture that we have in the classroom. So that's a shearing 1 unit to the right. For some reason, when you're asked questions in the exam about what does a matrix do geometrically, or what matrix represents this geometric transformation, the geometric transformation is never a shearing. I don't know why. Shearings are quite important, which is why I've also mentioned them in this little video. So I hope you now understand enough. If not, just go through this again and then make up some transformations for yourself, simple transformations you can describe in words, do the diagrams and see what the matrices are.